Welcome to Epitide 202. I am super excited about being here in person at reInvent this year, especially after missing out after last year. I think we have a fantastic story for you today. The agenda that we're going to go through is we're going to do some introductions first, and then we're going to get into how JP Morgan modernized its core risk management framework. And then we're going to talk about some key takeaways and some challenges that they faced. But before we get into that, I just wanted to talk about my connection with JP Morgan and Chase. My name is Ollie. I'm a AWS solution architect, and I'm dedicated to the JP Morgan account. And I focus specifically on corporate and investment bank and JP Morgan markets. And I feel I'm quite privileged to see JP Morgan go through their app modernization program, but also their journey to cloud. And I still believe that we're at the very beginning stages of a titanic shift to the cloud. And I wanted to start by referencing Jamie Dimon, who is CEO of JP Morgan Chase & Co., right in his 2020 annual report to his shareholders. And I quote, "We cannot overemphasize the importance of new technology today. Technology is built cloud-enabled, which means that the application and its associated data can run in the cloud. And this brings many extraordinary advantages. But the one I'd like to spotlight is the immediate ability to access virtually unlimited compute in the cloud." And personally, I feel that's a very strong message for Jamie to be sending to the business, but also to the shareholders. And I see this app modernization happen on a daily basis at JP Morgan. And I'm involved in the conversations, and I see the energy and the enthusiasm it brings to the application teams, product owners, developers, and engineers. And I wanted to give you a couple of examples of those application modernization stories. The first one is an application that processes 3 billion messages per day. And they were constrained by on-premise hardware. But by moving to the cloud, not only were they able to keep up with business demand, but they actually got ahead of business demand by using virtually unlimited compute power in the cloud. And this application team have taken their learnings, and now they're moving a whole suite of portfolio apps to the cloud. And this means that they can keep ahead of the business demand. The second story I have is an application team that ran their month-end reporting system on-premise. And they were struggling to meet their SLAs, which was running that report at the end of the month. But by moving that reporting system to the cloud, they were able to cut down their reporting time from 24 hours to around 11 hours. And when we asked the business, what does that mean to you? They said, now we can do more scenarios in our month-end report, which means that we can get better information back to the business so they can make more informed decisions. So I think these are two great stories. One, keeping ahead of the business demand, but two, by moving to the cloud, they were able to help create more information for that business. But I actually think we have an even better story for you today. And I want you to, in a moment, I'll be introducing to Michael Elliott, who is a managing director in JP Morgan Markets and platform owner of Athena. We'll also welcome Oana Nistoranu to the stage, who is the lead software developer. But before I introduce them, I just want to say that we're going to talk about this platform called Athena. Now, it's got nothing to do with AWS Athena. It just shows they chose a great name. And to that end, can I welcome Michael and Ioannis to stage? Welcome, Michael. Can you tell us about JP Morgan Markets and the role Athena plays in supporting that business?
Yeah, thanks, Ollie, and good morning, everyone. Ollie, I just want to say, first of all, I'm a bit disappointed you didn't have a live band and a Guns N' Roses riff for us coming onto the stage.
Next year, Michael, next year.
Yeah, so actually, our CIO, Laurie Beer, spoke last year with Andy Jassy at the reInvent keynote, and she said, everything we do at JP Morgan Chase, we do at tremendous scale. And that's certainly true of our markets business. JP Morgan is one of the world's largest trading firms. We develop financial products to help meet the needs of our clients. And those clients are large and complex, such as large asset managers, global multinationals, or institutional investors. And that means that their financial needs are large and complex too. And so to help serve that, we trade many different kinds of products, things like equities, currencies, commodities, interest rates. And we do that in established and emerging markets around the world. And these type of products vary enormously. They can be very simple things where we may trade hundreds of times per second, or they could be extremely complex derivative products. And those things are very tricky to model and computationally intensive to analyze. And the job of the Athena platform is to manage all of these trades after they're executed, to keep track of them through their life, and to provide the analysis that allows JP Morgan's traders to manage this huge portfolio. And that really comes down to understanding risk. What we mean by that is how is the value of a financial instrument change as the conditions around it, such as the state of the market, or the government interest rates, or client activity change. And often when we're doing these trades, we're doing them to help the clients manage their exposure to the financial markets, which means we take on risk ourselves. Managing that risk safely and profitably is really at the heart of any trading business.
So can you tell me about the architecture and history of Athena?
Yeah, because it's designed to support many different types of assets and businesses, Athena is designed around a set of core components that are meant to encapsulate everything that is common across products and geographies, and then a rapid change and development model that allows specialist technology or quant teams to deploy their own business solutions. As an example, the government bond market in Brazil has features that make it quite different than the US Treasury bond market. But the bonds themselves have a lot in common. So Athena provides a generic model for bonds with APIs that allow specialized types of bonds to be developed. Or if we're thinking about risk, the way that we calculate risk based on changing interest rates is mathematically quite different to how we might calculate risk based on the creditworthiness of a bond issuer. But the way that we orchestrate that calculation, manage the compute, aggregate and store the results is the same. And so Athena provides a risk framework that can be deployed for many different kinds of calculations. And while we're going to talk about risk today, Athena as a platform is much broader than that. We also use it for trade processing, we use it for signal generation, we use it for experimentation and idea generation in our quant teams. And just as JP Morgan's markets business is huge, Athena is pretty big too. There are 150 engineers developing the core frameworks that I talked about, and about 4,000 engineers across JP Morgan using those to deliver business solutions. We run over 1 million batch and real-time jobs per day and hundreds of millions of parallel risk calculations. Athena's not new. It's been around for over 10 years now. It's been growing in scale and scope over that time. And now we're thinking about how we set the platform up for the next decade of running our business. And that's where our adoption of AWS plays a big part.
Okay, so the next question I have is, with a successful business and a platform supporting that business, why embark on a massive project to AWS?
Yeah, well, everything we do is driven by our business needs. And in markets, businesses have been electronifying for many years, starting with very simple products like cash equities or currencies. And those things are almost 100% electronically traded now. But the trend is continuing, and we're starting to see more complex products like swaps and options also become largely electronic. And we know what happens when markets electronify because we've seen it before. What happens is trade volumes shoot up and ticket sizes come down, and the margins on each trade get smaller too. So we're going to need to be able to process in the future many more trades, do that much more efficiently. So we need to be able to add capacity without having to add linear cost or build more data centers. And at the same time as that, trading is quite a bursty business. You get big surges of activity at particular times in the day, like the market open or close, or maybe particular times in the month, such as when economic news is released or when futures contracts roll. And of course, we also have some days when the markets can be unpredictably extraordinarily busy, as they were, for instance, last March as the pandemic started to take hold around the world. On those days, it's the days when our clients need us the most, and we pride ourselves on being there for our clients when they need us. And so our tech platforms need to be able to adjust to these huge swings in load. So increasingly, the elasticity of a platform like Athena is really important to us. And finally, markets is a super competitive business. To stay ahead of our competitors, we need to innovate. And in particular, we want to get value from our data. Laurie spoke last year about Omni AI, which is our cloud-based AI ML platform. And we're looking for close integration between Omni and Athena to allow the trading business to drive insights from their data.
Thank you. So you just talked about Laurie there. Laurie presented last year at Andy Jassi's keynote. Why was that important, and what did her message mean to you?
Well, I think two things. First of all, it emphasized how important our cloud strategy was to the firm. And secondly, what a close partnership we have between JP Morgan and AWS. Because there's much more to enabling a systemically important institution like us to run in the cloud than just me and Ioana and our application developers. There's data center connectivity, there's cyber, there's regulatory, there's developer tooling, and a whole host of other things. So having support from Laurie and the cloud strategy she put in place across our technology organization has been key to what we've been able to do. Yeah, and Laurie did mention our Athena project in her talk, or at least she mentioned risk management. She didn't say Athena. As you know, that might have been confusing since you stole the name for one of your products. And we'd actually just gone live with a trading desk a few weeks before reInvent. So we'd been one of the early adopting teams at JP Morgan. We definitely hit some teething trouble along the way because of that. But having that strong top-down support really helped us push through it.
Awesome. So can you tell us how you got started on your journey?
Yeah, it actually started a couple of years ago. I took some time off. I took a short sabbatical from JP Morgan.
Nice.
And on my first day back, I had lunch with my manager, and we both agreed that we hadn't properly grasped the nettle on public cloud. And at JP Morgan, we had an idea of a cloud party. In fact, a colleague of mine, Gurdeep Jeta, talked about cloud parties at reInvent in 2019. So anyone who's interested in what goes on at a party can find that talk on YouTube. But what we do there is we get everyone that we need to accelerate the cloud implementation in one run for a week. So if our application team has a cyber problem or a networking problem or a regulatory problem, we have the right decision makers from JP Morgan right there to be able to resolve that. So what we did was we took a bunch of engineers from our Athena core platform team. We went to our technology center in Glasgow, and we spent a week at the cloud party. And in that week, we were able to get to a Hello World application in AWS, which Hello World for Athena means we can price a foreign exchange option.
Right.
So we still had a long way to go from there to being ready for production, but it really helped us get going and start to build momentum. We then had to choose our first use case. We needed something that was going to be really impactful to our business, but also something that was tractable and we could get our hands around. So we chose our end-of-day risk calculation. That's when we run a large batch of calculations at the end of each trading day to produce the official risk numbers for the firm, and also the baseline risk numbers for the next day's trading. So this is a really burst compute use case. We need a lot of compute, but we only need it for a couple of hours at the end of each trading day. Now, it's a little bit more complicated than that, because with a global business like ours, just as it's always 5 o'clock somewhere, it's always end of day somewhere too. But the key thing that we needed to do was to design a cloud-native risk framework in Athena and get that running in AWS. And that's what Ioana's going to tell us about today.
Awesome. So welcome, Ioana, and thanks for being with us today. Can you talk about what risk management is and what Athena Risk Management is?
Sure. Hello, everyone. My name is Ioana, and I'm the engineering lead on the Athena Core Risk platform. So I work for JP Morgan, and I'm based in London. So today's session is a migration and modernization story. We'll go over the risk use case in technical details, and we'll do a deep dive into the architecture, the design decisions we took, and the services we picked. And towards the end, we'll talk about the challenges and the successes we had. So let's start. Now, you've heard from Michael and Ollie how JP Morgan is one of the biggest financial institutions in the world. So as a result, the systems behind the scene need to operate at a very large scale. The Athena Core Risk platform is such a system. So it runs over 6 billion calculations a day across tens of thousands of jobs and across a very large compute grid. Risk scheduling is, in a nutshell, a very big distributed scheduler. It takes as input market data, which is data available on public exchanges. It takes as input risk models, which are the calculations we need to do, like present value or profit and loss, and the financial products themselves. And with all these inputs, the risk scheduler groups, batches them together, splits the calculations, and then parallelizes them on a compute grid of CPUs and GPUs. The results of those calculations are then persisted in a database or sent to an aggregator for our users. Before I go any further, I'd like to clarify a couple of terms. So when we talk about a job, we refer to a piece of work producing one to many risk items for a trading desk. Now, this piece of work can be split, decomposed into tasks. One task represents a unit of execution on one single CPU and is contained of multiple calculation items, which are let's say, the subset of the financial products. A task can have a cost and is not a US dollar amount, but it represents the resource requirement in terms of runtime and memory to execute that task. So now going back to our risk use case, we've seen that it's a compute-hungry workload with quite a spiky profile. So over a short period of time, we can see that our jobs are quite regular in terms of count and duration. As we extend the time horizons, we can see there are some anomalous peaks. They are usually due to unexpected market conditions, as Michael mentioned, or holidays. Now, for our business to sustain such an execution profile, they would have to either pay the cost for infrastructure, so they would have to pay for the infrastructure for the high peaks, or alternatively, they would have to accept that our systems cannot withstand a six-fold increase in load. So this execution profile shows us why access to pay-as-you-go on-demand compute is extremely attractive. It allows our business to be agile and flexible with changing market conditions and customer demand, while also being cost-effective. So as we identify the use case, we wanted to clarify a couple of principles that help us along the way, because the journey ahead was not easy. So first, we wanted to be use case and application-centric. So what that means is, we didn't want to view the cloud project as a data center or infrastructure project. We really wanted to focus on the application and the reasons and the impact to the business. We then wanted to use cloud native and managed services. So at JP Morgan, we actually love building software, and we have over 40,000 developers that do so. Now, with the cloud migration, we saw this as an opportunity to inject fresh new ideas into our application stack and also simplify our infrastructure by having someone else manage it. Then we wanted to design for resiliency. Now we were going to operate in an environment we could not control. And we also wanted to make sure our applications are horizontally scalable and use elastic and are able to use the elastic features of cloud. This is not a given, especially for on-premise applications, which run in a constrained infrastructure domain. And last and not least, we wanted to embed security by design and from the beginning, such that any developer on the platform, when they open a connection to the database, that connection is encrypted and authenticated. So Oli is going to go over the next steps.
Yeah, so here is a typical risk platform AWS architecture. And what this is showing you is an AWS account and what a line of business would have in that account. So each line of business has a single AWS account. They have a VPC. In that VPC, they have 2 subnets. One subnet is a routable subnet, which has a small set of routable IP addresses which are able to route back to on-prem. And then we'll see the larger non-routable subnet, which is the /16, which is a non-routable subnet which it overlaps with other VPCs. Now, where the compute sits is in that non-routable subnet, which means that it can then scale and burst up without consuming routable IP addresses. In the routable subnet, we have an application load balancer, a NAT instance, and the NAT is used to connect non-routable services back to on-prem. So, for example, the databases on-prem. Now, for inbound access, so for services on-premise accessing the risk control plane in the non-routable subnet, they will traverse the application load balancer. Now, why do we have a dedicated account per line of business? Well, there's a couple of reasons. The first is it provides simple chargeback. So each line of business then gets charged back what the cost of that AWS account is. The second one is really about operations. So each line of business operates its own account. And the third reason is they have different types of compute requirements. So one line of business won't impact the other line of business having their own dedicated account. And here we can see what the multi-account architecture looks like. And you'll notice that we have an AWS Athena core account. And this core account provides common services to all of the lines of business. And in there, we have the NoSQL database, which is a proprietary database that Athena run, which runs on EC2. And it connects back to on-prem and gets data required for the risk management framework to run. Oana.
So up until this point, we have a use case which would benefit enormously from access to the public cloud. We have a set of principles to guide us. We have integrated the JP Morgan and AWS data centers, and we have accounts and services which are ready for us to use. But as we mentioned, we wanted to be all application and use case driven. So as a result, we had to review the requirements for our software in depth and from the beginning to make sure we're making the right choices. So our expectation was that we'd have a scheduler which can support batch calculations, but it's extensible enough to handle real-time and event-driven risk calculations as well. We wanted a scheduler that is resilient to component loss and minimizes resource consumption. When we looked into more depth, though, we realized that our expectations were for our scheduler to actually be a bit smart about the job execution and focus on minimizing the end-to-end job duration and the cost, as well as the computational, the compute time for our jobs. Then we had very strict SLAs for our job delivery and risk deliveries. So we wanted a scheduler that is able to dynamically change the priorities at runtime such that our jobs would meet their SLAs. So we grouped our requirements into 2 categories. So the first one, compute management, that's pretty standard. You'd find that easily on AWS or on other service providers. It's a scheduler which provisions your compute when you need it and releases it when your environment is idle. The second category, we call it here smart task scheduling, is not so much. So when we went through the literature on distributed schedulers, the majority assumed that tasks are independent in their runtime. So what that means is that the more compute you have, the faster your job finishes. Now, for us, this was not the case. So we have this added complexity whereby if you have two similar tasks executed on the same process, the job finishes faster than if we had parallelized those tasks on two different machines. So we gave this concept a name, and we called it affinity, which represents, you can call it a metric, which is a metric representing the shared memory state required for tasks to execute in the optimum amount of time and memory. So let me give this concept a bit more color. Imagine you have a portfolio with investments in AWS and JP Morgan stock prices. You're very lucky, and you want to calculate the future profit you're going to make in a year's time. So you're looking in the future. So as you run you have to run quite complex mathematical calculations to see how much money you're going to make in a year's time. So you're parallelizing them on a compute grid. So if your calculations, depending, let's say, on Amazon, end up on a process which has already calculated the future price of Amazon, if they end up there, they will finish much faster if they landed on a fresh new node. So we looked through the data, and we draw a couple of graphs to confirm that this is the case. So let's take the example of a job that I just mentioned, and that can be parallelized across a compute grid. Now, if we parallelize it across 2 to 3 tasks, we can see the orange dot right at the top, which represents the end-to-end time of that job. So across 2 to 3 tasks, we end up with something like 8,000 seconds. As we introduce more tasks, so we parallelize the jobs more, the end-to-end time decreases, which is what you'd expect. But there is a sweet point around 15 to 20 workers, after which we can see there's no more impact to the end-to-end time of our job. And on the contrary, we see our CPU time, or total calculation time, going up. So at this stage, we face a bit of a pickle, I'd say. On one hand, we're super excited to access unlimited compute and power. But on another hand, if we're not careful, we can get a quite high AWS bill at the end of the month without any tangible benefit to our business. So at this point, I hope some of you in the audience are thinking of some solutions for us. So one of them could be, let's say, why don't we parallelize group the calculations together? So all of those depending on Amazon, they'll go on one task, and all of those depending on AWS will end up on a different task, and they end up sharing the same memory state on a process. It's a very good idea. But it has the challenge that if any of the calculations misbehaves due to all sorts of unexpected circumstances, like code changes, changing in market conditions, having this centralized decision-making brain, it becomes very difficult to rebalance the calculations at runtime. Now, other ideas could be, having a shared memory cache, such that different processes can access shared calculations from that cache. Again, a very good idea, which we also tried, but sadly didn't produce the results we were expecting because because of the sheer volume of data. That was one problem. And the second problem, the serialization and deserialization costs were extremely high. So we decided to take a different approach. So we moved away from a centralized scheduler that decides upfront how to split the tasks and then pushes them onto a compute grid to a pool model approach. So we gave it a name, and we called it adaptive task consumption based on affinity and cost. And we have workers that as they start up, they execute what we call a choice function. They assume a certain affinity, and they start adapting as they consume work. So we can see here in our queue that we have calculations enriched with an affinity and a cost. So we have, let's say, the orange ones are AWS, the blue ones are JP Morgan, dependent calculations. And each one of them has an estimated cost. our calculations are not evenly distributed. Some of them are very expensive and some of them are very cheap. So how it all hangs together. Now we'd have a producer of work, whose responsibility is to split the calculations to the most granular level and enrich those calculations with metadata, so the affinity and the cost, and push that calculation into a queue. We introduce the supervisor on that queue that continuously monitors the state of the queue and looks at the information like the SLA and the estimated costs, and then provisions the compute. As our workers come up, they run their choice functions and start consuming work from the queue. That's like we can call it a hungry hippo approach. And the result of those calculations end up in storage. If any of the workers were to be too hungry and sort of die due to out-of-memory errors or would take too long, we'd have a worker supervisor whose responsibility is to react to worker event failure and put the work back in the queue with a penalty to the cost. The result of that penalty means that on the next iteration, the work gets split even further across multiple workers. So as we're happy with our design, we decided to review if there are any solutions which are available for us to use. So we split the solution categories into two. So first, we wanted to review compute management options, and the second one, queue management solutions. So on the compute aspect side, we reviewed AWS Batch, which operates as a centralized scheduler which decides upfront how to split the tasks. And so we decided not to use it. We then looked at AWS Lambda, but sadly, for us, this didn't work out either because Lambda has very strict runtime constraints and also cannot be interrupted after it started. So we probably wouldn't have met our SLAs if we needed to interrupt the Lambda. And then we reviewed the differences between EC2 and Amazon EKS, and we found that we could develop our infrastructure on both solutions. Amazon EKS was more feature-rich and required less investment from our side. So we decided to go ahead with EKS. So we picked it because it was extremely flexible and supported a wide range of services like jobs, cron jobs, deployments, stateful set, daemon set. It is extremely easy to provision compute. So our application would just need to publish some metrics on Prometheus, and the horizontal pod autoscaler would just provision the compute as we need it. And then it provided information about the state of the pods. So we were able to build quite complex resiliency management. Now, when it came to our queue management system, this was quite a critical piece in our design and a critical choice because we had quite advanced work selection semantics. So we had to choose wisely. So we looked at SQS, and though we liked its simplicity, it actually operates more like a FIFO queue, and it makes items visible to a worker you can't select. Then we decided to even look at using RDS and implement a queue management solution based on RDS because it's quite powerful at selecting stuff. But we were quite worried that it would not cope with the load of having a large compute grid, selecting work from it, as well as we'd have to implement quite expensive locking mechanisms to make sure that's right. So in the end, we focused on Elasticache Redis. So what we found here, that we had a high degree of flexibility in the work selection semantics because Redis allows you to define your own structures with metadata, and you can implement all sorts of functions in Lua scripts. And it's single-threaded, which means that if you access the cache, the queue implementation from a very large compute grid, there's one single worker that executes at one given time. So it was very easy for us to use. So how it all hangs together. Now we have our risk jobs running on premise in our corporate data center. And instead of distributing the work on our own grid, it slices it into the most granular level, enriches it with metadata, which is affinity, cost, SLAs, and pushes it to AWS Varonis API, and lands that into our Redis queue. We have a deployment, EKS deployment, that is a queue supervisor, which monitors the state of the queue and decides, based on some smart heuristic, how much compute we need. The supervisor then pushes a metric onto Prometheus and says, and provides a desired number of workers, which are then picked up by the horizontal pod autoscaler, part of EKS, which provisions the compute by doing scale up or scale down operations. The worker deployment is the one that comes up, triggered by EKS HPA, and starts consuming the work. It adapts. It starts assuming a particular affinity. By executing Lua scripts, it generates results and then persists them into S3. If any of the workers were to fail, we have a worker pod supervisor, which listens to the Kubernetes Watch APIs and gets notified of failure events. And then that work gets put back into the queue. So we're quite happy with the implementation. So it's actually very easy. However, after 10 months of close design, development, and testing, we were able to run a couple of jobs. And that was, extremely, we were quite happy to see that running. Now, the challenge didn't come from this journey. The challenge came from being able to run a production system of billions of calculations and tens of thousands of jobs every single day and correctly for the majority of the time. So like with everything, scales breaks it and brings it down. So we had to take an approach to make sure when we go to production, we do so safely for our business. So the first thing that we did was to implement metrics and observability across every single component to make sure we understand what we're dealing with. And then, once we're happy with our dashboards and so on, we started doing repeated scale tests where we pushed the load of the system with every single test, and we saw where it breaks. So during a scale test, what would happen? We'd start from a very well-known state and start pushing more and more jobs and more load into our infrastructure and see how the network usage is performing, how our EKS control plane is handling the number of pods, how our nodes and pods coming up and going down, and how our databases are handling the large number of connections, both Redis and S3. So the results of some of the scale tests are added here. Now, on the compute side of things, we noticed quite quickly that the scale-up operations somehow seemed slow. So our EKS cluster was not able to provide us with enough compute. The blue line represents how much we needed, and the thick blue line below represents how many active workers and active pods we have provisioned. On the scale down, we were quite happy. We thought, oh, that's fantastic. Our desired number of workers and our active workers are matching. But when we started looking a bit into more depth in that, it actually was it was not as good as we thought. That was because our nodes were heavily defragmented on scale down. So what it means is that we have a large number of nodes with just a couple of pods running on it. And even though it didn't impact our application, it wasn't very efficient to run. We then tested the S3 integration and with millions of put and get transactions, and we got errors like slow down errors and that we weren't handling properly. We saw that the networks was quite under pressure by our load, and we learned about service limits in AWS and how you can only send you can only send a certain number of packets per second. We also reached limits of IP addresses in a subnet, and we identified several misconfigured NAT instances where we thought, our volume will be just 2 gigabits per second, but actually we reached tens of gigabits per second. And last, we follow the data flow. So we had databases both on-prem and AWS, and we noticed hundreds of gigabytes of data being pulled from our on-prem data centers to AWS. So we identified which databases we should actually replicate over. So all these repeated scale tests gave us the confidence to go live to production. So currently we have two businesses running on a daily basis, one of their most critical workloads in AWS, and across thousands of jobs. And we not only achieved on-demand pay-as-you-go compute for our business, we also saw significant benefits to them in terms of predictability of the results and the fact that they run just faster. So we were successful due to, I think, three key decisions we made. So first, the fact that we went cloud native with the guts of our system. So now it's easy and maybe to say, looking back a year ago, it sounds obvious, but at the time it wasn't. And it was a split-second decision, probably not to go with a lift and shift approach. Second, the fact that we done repeated scale tests and pushed the boundaries of our system with every single test was critical to the success. So we changed our culture, because now the entire team is looking for ways to bring the system down, which is great. And third, Athena is a platform. So we have a large community who invested years into financial models, and risk models and so on. So we wanted to make sure we minimize the rewrites for them and we take the majority of the heavy lifting.
Awesome. Thank you. And Michael, can you talk to us about some of the challenges you face meeting some of these business outcomes?
Yeah, I mean, it's one thing for us to build a new cloud-native risk system, but that's not enough. We also had to figure out how we would move all of our critical business processing over to it. So it's a bit like when people say you're changing the engine on the plane as it's flying along. So, but at the same time, we didn't want to be too conservative. We did want to get to production quickly. So we chose one relatively small trading desk to go live as our first production release. And we made sure that we had the ability, if we needed to fail that back and run it on premise if there was something that went badly wrong. That allowed us to learn about supporting a business in production in AWS. And then as we thought about how do we ramp that up to many trading desks across different businesses, we implemented game days, we went through the well-architected review, we ran a lot of scale tests, as Joanna talked about, and we also built a repeatable migration runbook that allowed our line of business application teams to start putting tens of desks live every month over a 7-month period. We also had quite a big challenge with data. Financial data is quite complex, highly structured. It's often time series based, and it's often stored in data stores specifically optimized for that purpose. It's not like truly huge global scale data, but there's quite a lot of it, and it changes quite quickly. And as a bank, our whole business is built on trust. We're overseen by many different regulators, and so protecting our data and that of our clients is paramount for us. We also had to think about the architecture that you showed earlier. How would we have some data that was shared amongst all of the different businesses using the Athena platform, and then some data that was individual to those businesses, and how we set that up among the different AWS accounts was just quite a different thought process for us than it had been on-prem. So that took a while to figure out.
Okay. So how did you work out what data you could move and what data you couldn't move?
Well, we started, first of all, by engaging with our business sponsors to make sure that they understood from the start not only what the benefits of this cloud adoption were going to be, but also what the technology risks were as well. We then worked with other teams across JP Morgan, our existing cloud projects, to learn from them with our cyber and reg and information security teams, to understand what we could use that had already been built and then what we would have to change for Athena's use case. But getting that first conversation right was really important to being able to have those subsequent ones. So we had a real risk-based view of the commercial benefits of the work. It's super important to us to be able to understand our technology risk in AWS based on facts. So we need to know what data and code is living in the cloud, how long it's been there for, and what it's going to do. We especially need to know which business processes and jurisdictions are impacted by that. Financial services is a heavily regulated industry, and as a global platform, Athena falls under the jurisdiction of many, many regulators around the world. So we had to be able to prove to ourselves and our internal compliance teams exactly what was running. So we had to instrument all of our pipelines in our production environment to be able to evidence that. And finally, we had to decide to be pragmatic. AWS was new to us. Athena is a really big platform. So in some cases, we decided not to move our data just because it was simpler not to do so. We would call back to our APIs on our on-prem data infrastructure. That allowed us to get live more quickly.
Okay, and can you tell us how you handled the operational transformation?
Yeah, that was a big challenge. Yeah. It was a big challenge, and I don't think we really grasped it early enough in the project how big a change it was going to be. Our application support team were really used to supporting the Athena application, but on-premise, all of the infrastructure is supported by our tech infrastructure team. So supporting the whole stack was new for our prod support team. So they needed to learn, and they needed to learn by doing, but obviously they couldn't do that in production. So we invested in the game days where we would build a production-like environment, and Ioana and her engineering team would deliberately break it, and then we would have the SRE team try and figure out and fix what had gone wrong. We also made sure that our SRE team were right in the well-architected review, and also that they drove all of our scale tests so they could see how the system behaved under load.
Awesome. Okay, so knowing what you know now, how would you have done things differently?
Yeah, I mean, I've learned a ton through this process. It's totally changed how I think about cloud for JP Morgan and markets. And I think anyone who's thinking about what your cloud strategy might be, if you're thinking that through before you've actually taken a real business critical workload into production, there's probably going to be a few things that you'll get wrong. As an example, at the beginning, we put too much abstraction around some key AWS services like logging and telemetry. We were worried about portability and multi-cloud portability and being locked into one vendor. But the cost of that was it really slowed us down. So we changed our approach, and while we still made sure our application architecture is portable, it's Kubernetes and Redis and virtual server, we went much more native with a lot of those supporting tooling, and that allowed us to move much more quickly. I think we didn't early enough realize the upskilling that would be required in the team. So we had a really good engineering team, and we're used to supporting a platform that thousands of developers use. But we were underprepared really for what we would need to learn to make the best of AWS. So I think earlier investment in learning and certification and maybe a couple of experienced hires as well would be something I'd do differently. And finally, our partnership with you guys in AWS. At the beginning of the project, we treated you like any other vendor, and I hadn't realized what value you could bring with your knowledge and experience of cloud best practices. So now, Ollie, you've become like a key part of our team. You're at the table in all the design and project discussions.
Yeah, it's awesome. The partnership is great. And so, Ioana, can you tell us about what you and your team are doing next?
Right. It is very important for future success to be able to continue optimizing both on costs and runtime. So we have designed our platform to be interruptible, and we're currently running Spot in non-production environments. So we're very keen to run Spot in productions once we've analyzed the potential impact of Spot interruptions on our SLAs. We're using GPU and other accelerators on premise, so we're very keen to move these workloads to production as well. However, the challenge there is how we can integrate EKS and our rescheduler with GPUs of hybrid CPU and GPU node. And then you've seen from our scale test results that we don't quite scale fast enough. So we're looking with you, Ollie, and your partners at AWS at using Carpenter. So there are a couple of sessions, I think, going on this week. So for those that do not know, so Carpenter, it's an autoscaler solution for Kubernetes, which would allow improve pod allocation and faster pod allocations on nodes by using directly EC2 APIs instead of auto-scaling groups.
Awesome. Michael, what's next for you?
Well, the use case that we chose, which was risk, was really about availability of compute and elasticity of compute. And we have lots of other use cases in Athena that would also benefit from that, such as trade reporting. As well as that, Athena has a lot of real-time workloads, event-driven workloads, such as processing a trade into our books as soon as it's executed on the exchange, or calculating risk for our traders intraday so that they can make prices to clients and hedge their portfolios. So we're really interested in function as a service for that use case, but there's a lot of interesting questions about how we might integrate something like Lambda with Athena. And we're also, as well as access to compute, as I mentioned earlier, we're really interested in access to innovative products in the cloud. So we've been working with our AI/ML team to integrate machine learning models that are deployed in SageMaker with the Athena cloud deployments. So we think there's some really interesting use cases for our business for machine learning models, but also for optimizing Athena itself. So for instance, we're looking at a reinforcement learning model to try and auto-optimize the affinity and bucketing calculations for risk that Ioana talked about earlier. But key to all of this really has been our close partnership with the AWS product team. So I think Carpenter is a great example, being able to work closely with the EKS product team so they understood what our requirements were and what our problems were and could feed that into their roadmaps and product development has been huge for us. Yeah. So it's really, it feels a little bit like early days. We've achieved a lot, but there's so much more that we can do in accelerating Athena's journey into the cloud. So our team is growing really quickly. We're hiring. So anyone who's interested in that or in anything else we've talked about today, please come and find me or Ioana or any of the JP Morgan team after the talk.
Excellent. Thank you, Michael. And the hoodies are down there with we're hiring on. So let's get to the key takeaways then. So these are the key points that I'd like to talk about. So the first one is stakeholder support from the top down. And I touched on it at the very beginning with Jamie Dimon mentioning it to his shareholders in his 2020 annual report. And I think that sends a strong message to the shareholders, but also to the business. Secondly, we saw Laurie Beer on stage last year emphasize why the app modernization program is so important to AWS. And today we've heard it with Michael, driving the adoption of cloud in JP Morgan markets by modernizing the Athena platform. Secondly, I think anyone who's just setting out to get on their journey, just start, just get your hands dirty. You learn by doing, and you start building up skills in your ecosystem within your teams. Also keep trying to innovate. Don't just lift and shift. Get into the cloud, innovate, and start improving your platforms. But also don't stop optimizing. Try and drive down that cost. We heard it earlier, trying to take more advantage of Spot, but optimize and innovation is key. And there's another one, scale tests. So you've heard a lot about scale testing. It was a huge moment within the move to AWS where the Athena platform were hitting some problems at scale. Scale breaks everything, and by running at scale, you learn new things. If you don't know if you don't know why you need to scale test, then you need to scale test to find out what happens to your application running at that scale. And lastly, it's an obvious one, but take time out. Take time out to go through certifications and also take advantage of the huge AWS ecosystem. And that's pretty much it. My final words are to thank Michael and Ioana for their impressive march to AWS. And we look forward to continuing our partnership with you guys. But lastly, thank you to you guys. Thanks for listening today. And I hope you found this talk interesting. Thanks for coming and enjoy re:Invent.